So today we'll wrap up BJTs, hopefully. Got all those things to run. Still remember all these equations? What are these ones? When we learn IC equals to IS times E, VBE over VT, right? And IC equals to beta times IB, and alpha times IE equals to IC. So because you know this, and plus IE equals to IB plus IC, so you can derive it and find out alpha is beta over 1 plus beta, and beta equals to alpha over 1 minus alpha. Right. So for this problem, which equation do you want to use? VBE is given, and at that moment you got IC, which is 1 milliamps. So find out the VBE at a different IC. Excuse me. There are two different ICs, so you need to calculate them separately. So use this equation, and you plug in this IC over here, so get 1 milliamp equals to IS times VBE, which is actually 0.7 volts, over 25 millivolts, which is VT at room temp. And now you are trying to calculate the VBE when IC is 0.1 milliamp. Combine these two equations. IC is proportional to the junction cross-sectional area, temperature, and the width of the base. All these parameters is not a variable; it's a constant. Consider as a constant over here, and you do not have to calculate it, even though you have two variables, two equations. You are able to calculate it, but you don't have to. Just do a division on the two sides. So left divide by left, right divide by right. So it's going to be 1 milliamp over equals to this 5 millivolts over IS canceled as is 10, and you're getting E 7 minus VBE over VT, which is 25. Let's just write 25, and natural log on both sides. So you can calculate for VB here, use this equation. Okay, you can just Google for a natural log calculator online. So what is log, natural log 10? I don't know, somewhere around 3, less than 3, 2 point something, I guess. And then calculate for VB. Okay, that's how you do this type of problem. Example 1. Any questions? So next week we have homework 2 due on Wednesday, and we'll have a quiz on Wednesday, and we'll have a midterm exam on Friday. So I'm going to give you a review for the exam on Monday. Okay, so not too many new things to be covered next week. Will be a quiz and a homework due and midterm exam. Am I correct? Is that Friday? It's Friday? Okay. It's 1 hour. No, 55 minutes, right? Just during the class. And should be closed book, closed notes. I think that's it. Any other questions regarding that? Okay, we'll cover more details about it on Monday. Where to get started? IE is IB plus IC, and it's asking for alpha, and alpha is, since you know this, right? And the typical value for alpha is somewhere around 0.9, because IC and IE are pretty close to each other. Due to the IB is tiny, we can compare IB and IE. It's just in the microamp range versus a milliamp range, right? So you know that IB, so alpha, so first let's calculate alpha. Alpha equals to, according to this, so that is IC over IE, right, from here. And IC is IE minus IB over IE. No, IC is IE minus IB, and this is IE. So that will be 1.46 milliamps minus 14.46 microamps and over 1.46 milliamps. So we can find out alpha, and which is 0.99. We can find out actually alpha is very close to 1. So what is beta? Beta is a function of alpha, right? So what is beta? You just want to remember this really clearly every time, right? Just memorize all these equations. It's alpha over 1 minus alpha, like this. So it is 99 times. And remember the typical range for beta is 50 to 200. If you buy a BJT, NPN BJT, it's going to be somewhere around this. Normally we use 100, but sometimes it can be 200. So 99 looks correct. If you calculate for beta, which is like 1 or 2, probably your calculation is wrong. So it's a quick method to check it really quickly. Okay. Alpha, beta are calculated. So what is IS? I'm going to use this equation. IC equals to IS times E to the VB over VT. So IS is E, what is VBE? 0.7 volts over 25 millivolts. that's this part, over IC. IC is, have we calculated IC? Not yet, it's actually over here, over IC, right? Which is E 0.7 over 25 millivolts over 1.46 milliamp minus 14.46 microamps. We can find out IC. Yeah, if you're using milli, just keep using milli. That clear? It's number 2. Do you need me to calculate this, or you are fine with it? You're fine? Yeah, just use a, if you don't have a calculator, just Google it. Just Google calculator, right? Find a calculator, calculate this. So you can use, what's the typical number for, wait, did I make it right? Oh, it should be IC over this, sorry. Okay. What's the typical number for E? 2.7 something? Right, it doesn't have to be super accurate, right? Just find out the number for E. So the IS is normally very tiny. If you calculate this, this is somewhere around 10 to the negative 15 amps. For Pnp example, and this is grounded. And this is 2 milliamps. So that's a Pnp transistor. So the difference is the arrow is pointing inside the transistor in terms of the symbol. So you can tell the difference between this one and the NPN transistor. And the arrow is always at the emitter. So here's emitter, here's the collector. And so the 2 milliamps is going to be the IE. Is the largest current, IE. So this is asking for VE and IB and the IC. So beta is given, beta is 50. And IS is also given, which is 10 to the minus 14 amps. Yes? So the Pnp transistor follows the same rules as all the equations you have used for the NPN transistor. So IE will be the largest current, and it's being split into 2 branches, which is IB and IC, according to KCL, right? So one current flows down, and it's being split into 2 currents. One getting to the base, another one getting to the collector. So where to get started? It follows the same rules. Since you have IE already, and you know alpha times IE is IC, so you can actually calculate for IC. So IC is alpha. What is alpha here? Do you know alpha? It's not given, but you know beta. So alpha is beta over 1 plus beta. What is IE? 2 milliamps. And beta over 1 plus beta is 50 over 51 times 2 milliamps. going to be very close to 2 milliamps, which is 1.96 milliamps. So got IC. If you know IC, can you get IB? Yes, because IB equals to IE minus IC, which is 2 milliamps minus 1.96 milliamps, which is 0.04 milliamps. So IB is calculated, and IC is done as well. So VE, what is VE? So the voltage at this point compared to the ground. And the base is actually grounded, so VBE, actually for the PNP, is going to be VEB. So VEB has to be larger than the threshold voltage here to turn it on, right? That's for PNP, but for NPN, it's VBE. For PNP, it's VEB. VEB has to be larger than the threshold voltage to turn it on. And because B, the base terminal is already grounded, so whatever VE is going to be the same as VEB, right? So VE equals to VEB, and follow the same rules. So IC equals to IS, VEB over VT. IS is given, IC has been calculated. So VEB equals to what? You can move this to the left. Let's do it. Do not skip all the steps. So this one can be written as IC over IS equals to E to the VEB over VT. And natural log on the both sides, you're getting right, and move VT to the left. So VEB, which is VE, equals to VT times natural log IC over IS. So done with that. Why do we need a PNP? Everything is good for NPN. Why do we still need a PNP? Like the NMOS, right? We have NMOS, but why do we still need a PMOS? Pulling the output too high to VDD, right? Is better at pulling voltage too high, same as PMOS. And the VBE is from the base to the emitter. So VBE is not the voltage from the base to the ground. Keep in mind. And that's the emitter resistor. So this is asking you to find out the quiescent point. Let me explain this to you guys. Or Q point. It's actually the DC biasing point. So where do you bias your NPN transistor? If you look at the IV curve, it looks like this. You can bias this transistor at any point, and it's going to be the Q point. You can bias it here, you can bias it here, right? Everywhere you like, but these will be the Q points. We have our load over here, and we can draw a load line. I'm going to show you why the load line looks like that. For example, since this is not original connection for the NPN transistor, you have a resistor here, you have a resistor here. And let's just look at here. If you have, this is VCE versus IC, right? If you have VCE, which is a voltage drop across the collector and emitter, to be 0 on the curve, what is IC? So when IC equals to what? No, when VC is 0, which means it's actually a wire. IC equals to VCC minus, because there's no voltage drop over here, so the only 2 voltage drops will be RL and RE. So the total voltage is VCC, and you just use VCC minus voltage drop over here divided by RL will be the IC, right? Is that correct? Yeah, there is a little current being injected to the base, but we just calculated according to the Ohm's law. I don't think there's anything wrong with it. It's tiny. Okay. So IC equals to VCC minus VRE when VC is 0. So we are ignoring IB right now because the beta is high and IC is pretty much close to IE. Is that clear? If IB is huge, you cannot do that. It's not a voltage divider anymore. But now you can assume they have a very similar current. So VCC minus RE, VCC minus VRE will be the voltage drop across RL because VC is 0. Over RL will be the current flow through RL, which is exactly IC. So you can actually label here as VCC minus VRE over RL. That's the IC max. That's the maximum IC it is able to achieve. So what about when IC is 0, what is VC here at the x-axis? If IC is 0, no current flows through the channel, so no voltage drops. You totally have VCC. So what's going to be dropped across VCE will be VCC still. So when IC is 0 on the x-axis, when IC is 0, VCC will be VCE, right? Any questions? So we're just trying to find out the 2 points. What's the maximum IC and what's the maximum VCE? Because these are the 2 extreme values which may happen for this transistor on this curve. So here's the IC max, which is this. And what is the VCE max? When there's no current flow through it, the voltage drop here will be exactly the voltage drop across the transistor because no voltage drops across the resistors. So here will be VCC. And if you draw a line, that's called the load line. And all these points are the Q points. And there will be many of them. but you want to pick up the best Q points, which is right in the middle. So if you have an IC like this, you want to pick up something in the middle. The reason is, for example, like this, you have here's your signal, original signal, like whatever you have done for the op-amps lab. Here's a signal, for example, this is 1 volt and 1 volt oscillation to the top and bottom. And you have a power supply like this. And here's where the op-amp is being biased. You have 5 volts, 0 volts, and this is 1.2 volts or something. No, 2 volts, let's say 2 volts. Right? If you amplify this signal by twice, and you're getting, this is 2 volts, this is 2 volts. Right? But you cannot amplify this even further because it's going to be distorted. It's going to be clipped. If you amplify this by 4 times, definitely you can get, or 3 times, for example, you're getting 3 volts here. It's going to be clipped at the bottom. This is not being biased correctly. So if you want to bias this transistor correctly, you want to bias it in the very middle for the DC point. If an IC max to be this value, you can calculate it first, and then just find out whatever in the middle will be the best IC. So you can bias this transistor correctly in the middle. When you're amplifying a little signal, like audio signal, a small, like in millivolts voltage input, you can get a larger swing on both sides of the range. So when VCE, for example, if you bias your transistor here, right? And so your VCE can swing. For example, VCE swing like this in these 2 ranges. And your IC will swing like this. Just follow all the curves. Okay, keep in mind one point. Find out the maximum IC first, and then divide by 2. Right, so that's a appropriate Q point for the transistor. So the Q point include IC, IB, because if you know IC, you are getting IB just over beta, right? If you know one of them, you can calculate all of them, like VBE, VCE, so all these DC points. But if you got one, you can get all of them actually, right? But whenever it's asking you to get the Q point, definitely just calculate for one of them and then find out the rest of them afterwards, right? So this circuit is provided like this, and it's asking you to design the circuit, which means you need to calculate for all these unknown values. So the load resistor is definitely given, because that's the load you are going to drive using this amplifier. And VRE is also given, it's 1 volt. So it's asking you to calculate for R1, R2, and RE. Whenever you find out the appropriate Q point for this guy. Because right now all these resistors are not given. So you don't know what is IB, what is IC, you just want to calculate it, you just want to design IC. So whenever you are designing an amplifier, you are designing the DC point. So you need to know what is IC. So since IC is actually biasing this transistor to a specific Q point, right? It's IC, Q point, IC in the middle, Q point. So let me write down the conditions. So RL, which is given, that's a load, so that's given, 1.2 kilo ohms, and VCC is 12 volts. VRE is 1 volt, beta is 100. All right, so these are the values provided to you. think about this for a minute. Since you know all these equations, right? Where do you want to get started? So for something like this, we just assume VB is 0.7 volts. We're not trying to calculate for all different values of VBEs. So IS is not given. Right. One rule of thumb, which is, so these two resistors is a voltage divider, directly introduce the voltage to the circuit. So this is actually providing a biasing voltage to this transistor. And you do hope that the current flows in this branch is not being shunted too much to the base. Because whenever this is, if you have a current flows here and the amount of current flows into the base here is comparable to this current, then whenever this is changing, you are going to have a different voltage value here. So you want to keep this one pretty robust. And you want to keep the current flows through here a lot higher than IB. So IB will be a little tiny current change, but this current is huge. So whenever this is changing, it's not affecting this too much. So you can bias this transistor to a reliable point. So let's assume IR2, which is 10 times RB. So just use the same value, use the same ratio in the homework assignment. So assume, so we are designing this, right? So we are designing this. Nobody knows what are the currents. Okay, what you know is you have a load, which is this, and VRE has to be 1 volt, and here's a power supply, and that's it. So I'm going to design the circuit to bias it at a certain IC, right? And also find out the resistors to make that happen. So you want to design the combination of the resistors to make what happen? To make this happen. IR2 equals to 10 IRB. So the current flow through here is a lot higher than this. Like a water pipe, you have a lot of water here, so whatever being changed over here is not actually changing the status of the current here significantly. So it can provide a very stable bias. And I mean, why? But I'm saying, like, if you have a lot of current here, whenever this is changing, it's not changing the voltage here too much. Why? Why that? So imagine you have a huge pipe, huge water pipe. It's flowing water from top to bottom, right? And a little tubing and trying to steal some water from there, right? If that water volume from that tubing changes a little bit, is that changing the water volume in the huge pipe significantly or not significantly? Right? Not really much, right? And sometimes can be negligible, actually. If you have a little tubing and you are trying to steal water from the tubing with the same tubing, then you can imagine whatever changing here is going to change the current flow through the main tubing very significantly, right? So that's a concept. It's the same as here. But whenever the current is being changed, as a voltage here at this point, I want this voltage to be stable because I want to bias this. I want to provide a stable VBE here. I want this voltage to be stable. You have a stable VBE, you have a stable curve. It's not jumping to different curves too much. So a stable voltage here. And the voltage here is actually the current times the resistor. And the resistor, if you design it, you cannot change it. Right, it's already in the circuit. So the current change here is going to change the voltage a lot if you have a comparable current to IB. Right? The voltage here equals to I times R2. Right? And the voltage change, the delta V will be delta I times R2. And R2 is not changing. So the delta I is going to dominate delta V. So I want the delta I to be small. So delta V will be small. Okay? So let's assume this 10 times. IR2 is 10 times higher than IB. And what's next? IC max. So if you get IC max divided by 2, you get ICQ. Q point for IC. So how do we get IC max? Can you find out IC max just given whatever here, all the conditions here? So what is IC max? IC max equals to VCC minus, since VR is given, which is 1 volt, over RL, which is 12 volts minus 1 volt over RL, which is 1.2K. So here's Imax, which is 4.58 milliamps. So ICQ equals to what? Nobody told you what is ICQ. What's the DC biasing point? You are designing it, right? So on a bias, ICQ right in the middle. So ICQ equals IC max over 2, which is 2. Oh, this is wrong. Sorry, this should be 9.2 milliamp. And if you calculate this, you are getting 4.6 milliamp. That's ICQ. You should feel a lot better now because IC is already calculated, which means you already know where you want to bias this NPN at, right? So IC is given. You can easily calculate IB because beta is given. So IBQ, which is ICQ over beta, that will be 46 microamps. Is that correct? Yeah, 46 microamps. What's next? I know IB right now. That's a DC biasing current for this NPN. So I know where this NPN is being operated at in this curve, right? I know it's somewhere here. And since we are assuming IR2 is 10 times IRB, it's not IRB, it's IB actually. There's no RB. IR2 is 10 times IB, which is 10 times 46 microamps, which is 460 microamps. So you'll know the current flows through R2 right now. But you are designing a circuit, you want to know R2. So what is R2? What can you calculate for R2? I know the current here already. Since I don't know the voltage here, so I cannot calculate for R2. But look at here. You got 1 volt from ground, you got 1 volt jump. And now from VB, you got a 0.7 volts jump. So what's VB? What is VB? Or VR2? 1 volt jump, 0.7 volt jump. So this point is actually 1.7 volts. And so R2 equals to VR2 over IR2, which is 1.7 volt over 460 microamps. I can calculate for that, which is somewhere around 3.71 kilo ohms. What's next? I just need to design the circuit. Now I already know R2. I want to know R1. So what is R1? Can I calculate for R1 easily? Since you know the current flows, we are talking about DC biasing, right? There's no AC current. So what's the DC current flows through the capacitor whenever it's stabilized? Turn on the switch for a while. After a while, what's the DC current flows in that branch? DC. 0. It's an open circuit. So current flows through here from the source, right? The source is providing a current. And then 2 branches. That's 1 times IB. That's 10 times IB. What is this? 11 times IB. I got 11 times IB and 1 times IB here and 10 times IB here. So IR1 is 10 times IB plus IB, which is 11 times IB, which is, we need to know IB first. Since IB is, we know IB? Yeah, this. Yeah, so it's 11 times 46 microamps, which is oh, I didn't calculate it. You can calculate it, right? It's pretty easy. 11 times IB. What is that? So it's going to be 40. 506, like this. And why do we want to calculate for R1? Because we want to calculate for R1 so we can design the circuit. We can plug in the R1. So we know IR1, we know VCC, we know VB. You know the voltage drop and you know the current, so you can calculate for R1. Calculate for R1. So R1 equals to VCC minus VB over IR1, which is 12 volts, I guess, minus VB is 1.7 volts over IR1, which is 506 microamps, and R1 is somewhere around 20.45 kilo ohms. So R load is given, R1 is calculated, R2 is calculated, and only have RE left. So what is RE? I know RE is VRE is 1 volt, and I know IC, I know IB, so I know IE. Okay, so VRE over IRE will be RE. You know the voltage drop, you know IE, so you can calculate for RE. Do we know IC? We know IC is this. And we know beta, so we can calculate for IE. Since IE is 1 over alpha times IC, which is 1 plus beta over beta times IC. And it is 101 over 100 times IC is 4.6 milliamps. So IE is very close to this, right? It's 4.63 milliamps. So RE equals to 1 volt over IE. 1 volt is given, so keep in mind. You are thinking like, how do you magically get a 1 volt for VRE? It's given. So 1 volt over IE, which is 1 volt over 4.63 milliamps. It's going to be kilovolts, kilo ohms level. So that is 2, actually not, it's lower than 1 k ohms, 216 ohms. So in conclusion, the circuit has been designed, right? So in conclusion, R1 is 20k, R2 is 3.7k ohms, and RL is given, which is 1.2k ohms, and RE is 216 ohms. So these resistors are calculated, so you can directly plug in here to design the circuit. You can bias this guy at the Q point, which is in the middle, which is the best place to bias it, so you can get the largest swing. IC plus IB, no, you can directly use alpha, because IC and IE has a alpha as a factor. So you know IC has been calculated, so you can directly use this times this, you can get IE. Which one? Current flow through it where? Yes. Yes, IB plus IC is same as IE. So why is it? How this is calculated? Because the original equation was IE is IC plus IB, right? And IC is beta times IB. Or you can say IB is IC over beta. Okay, and beta you can find out from the data sheet. So this is actually 1 plus 1 over beta times IC, which is IE. So beta over 1 plus beta times IC is IE, and that we just use a different symbol to represent this guy. That's alpha. No, that's 1 over alpha. Because IE equals to IC, alpha IE equals to IC. So you can directly calculate IE from IC, and you can directly calculate IC from IE by using alpha. And you can use beta to connect IC to connect IC with IB. Just derive it by yourself. Do this so you can remember all of the coefficients for all the currents. And we're done for that circuit. And now let's get another one. It's pretty important. Determine, as example 5. Determine the Q point and find the maximum peak value of the base current for linear operation. And beta equals to 200. So here's the circuit. VBB, which is 10 volts. Here's RB. Here's 47 kilo ohms. Here's RC equals to 330 ohms. And this guy's 20 volts. So find out the Q point. And this has been biased by these two voltages. And it's already being biased at the Q point. So you cannot design it because it's already being biased. Since this voltage is 0.7 volts. So you can calculate IB, which is VBV minus VBE. This voltage minus VBE, so you can get a voltage across RB and over RB. So you can find out VB is 10 volt minus 0.7 volt over 47K, which is 198 microamps, and that's IBQ. So this transistor has been biased by these two voltages, and here is the Q point for IB. This is 198 microamps. If you know IB, and you can find out IC, which is beta times IB, it's going to be 200 times 198 microamps, which is 39.6 milliamps. So that's ICQ. So what is IC max on the curve? You know, all these curves. You have the load line, because you have a RC or RL, doesn't matter. You have a load line. Here's IC max. Here's BCC, VCE over IC. So there's a Q point. So the Q point is 39.6 milliamps. And how can you know what's the position of this guy, of this current? Find out the Imax. So IC max is 20 volts minus when VC is 0, because here x-axis is 0, so you can find out IC max. It's going to be 20 volts minus VCE, which is 0 volts, and over this, I think this is RL, not RC. Sorry for that. RL, just call it RL. Over RL, which is 20 volts over 330 ohms. So what is that one? 60.6 milliamp. So you can see this value, this maximum value, is a little bit larger than twice as much as this guy, smaller than 2 times this guy. Because 2 times this guy will be 70 something. So you can imagine this is actually being biased a little bit closer to the Imax. All right, so it's going to swing like this and cannot reach the bottom. So the maximum IC will be this, but not this. So 39.6 milliamps is closer to the cutoff, closer to the Imax. Sorry for that. So the peak IC is here, which is 60.6 milliamp minus this. Let's call it ICP. So in that case, this is somewhere around 21 milliamp. So it's asking for the maximum value for the base current. So we know ICP. So IBP is ICP over beta, right? So it's 21 milliamps over 200. So you can find out the maximum base current swing, which is this. I got one more example left, but I couldn't do that today. So I'm going to use probably 20 minutes on Monday to do this. pretty much done for BJTs. Okay. See you next week.